Hey guys, today we're going to look at capacitors and also solve a bunch of examples that you might encounter in the fundamentals of engineering exam. So I've shown here basic construction of a capacitor. It's a component that stores energy in an electric field. So what's going to happen is I've shown here, I have my parallel plate capacitor right here. It's got two metallic plates. It's separated by a dielectric medium. Now, this dielectric medium is something that does not conduct electricity. It can be glass, air, anything. And so when I connect these parallel plates of the capacitor to the terminals of a battery, so I'm going to have some charge. So I have positive charge on one side and negative charge on the other side. And that is going to lead to the formation of my electric field lines that I've shown here in the yellow. So that is how we can say the capacitor stores energy in the form of an electric field. Now, to solve any problem on capacitors, we need three main formulas. We make use of them. So the first one relates the charge on a capacitor to the voltage. And if you look at it here, there's some kind of charge on the capacitor. So what the first formula says is the charge on your capacitor is directly proportional to the voltage that you apply across it. So if you have more voltage, you have more charge on the capacitor, and that is related by a term called capacitance. So this C term is called capacitance, right? Pretty straightforward formula. So, and it's also like common sense, the more energy that you supply to the capacitor, the more charge that is accumulates on it. And because we have charge, the capacitor also has energy, because charge creates an electric field, and the electric field has energy. So the energy here in the second formula relates to the voltage supplied to the capacitor as E equals half times capacitance times voltage squared. Now, if you don't have the voltage, but if you have the charge, it can also be written as half times capacitance times V can be written as charge by capacitance, so Q squared by C, and if you C squared, so if you cancel out the C's, you get half times C squared. So either of the expressions can be used to solve our problems. And we come to the last formula that we'll probably use in our solving our problems in the FE exam, is known as the current voltage relationship. So let me write it down here. All right, that's some messy handwriting. All right, so this relates to the voltage of a capacitor at a given time. So if I have a capacitor here, let's consider this capacitor. At time 0, the charge on this capacitor is going to be 0 because I have not connected any, right? So I have not connected any component, any voltage source to this capacitor. So at time 0, I'm going to write it here, V at 0 is going to be 0. And let's say at time 0, I hook it up to a voltage source. And the voltage across the capacitor is going to rise like this. So this is my time, and this is my voltage. So at 0, we have 0. And as time progresses, the voltage across the capacitor rises like this. This is the characteristic equation of a first order system, and it follows a certain time constant. I'm not getting into that, mainly because this is not in the topic for our video, but just know the voltage across a capacitor rises with time like this. All right, so that is the formula right here. So voltage at time t, so if I have, let's say at a certain time t, I want to find the voltage. So that voltage is given by the initial voltage. So this V0 is my voltage at time 0, plus 1 by C times integral of current, capacitor current times, yes, sorry, not no times, just 1 by C times integral of the capacitive current up to that point. So what it basically means is, let's say we have the circuit right here, and if I hook it up to a power supply, we know that this there's going to be some flow of charge, and it's going to charge the capacitor in this way, right? So it's going to charge the capacitor. So at 0, it's 0. At Vt, we have a certain voltage Vt. But in case from time 0 to t, if there is an ammeter, it may read a flow of charge. So that is IC here. That is what and we sometimes try to find out. And if you look at it closely, this term is nothing but the charge. So the charge Q is nothing but the integral of current over a period of time, right? So those are some basic formulas related to capacitors. Let's go into applications. So applications and rectifiers. So capacitors for DC current are open. So if you have a DC current, the capacitor, if you have a DC voltage source, the capacitor behaves like an open. But if you have an AC source, the capacitor behaves like a short circuit. So what you can do in our rectifiers is we're trying to convert AC to DC. So we can use capacitors to sort of bypass the AC so that we get a pure DC at the output. Another same application that can be used in capacitors is in ripple correction. So let's say you have a load and it's powered by a DC supply, and then sometimes your DC supply can fail. So in the case your DC supply fails, your capacitor is still charged, even though this part that I've shown in the box, let me use a different color for that. So let's say the part in the red box fails, the capacitor still can power the load. So there's no ripple, so the voltage to the load is pretty much a steady DC. There is no ripple. So it's going to be a steady DC. All right. And the last application is in power factor correction. So if you have, as we looked at it, a capacitor acts like an open for DC and a short for alternating current. But in large buildings, the capacitor, if you have a lot of inductive load, what's going to happen is, let me show it right here. So if this is your voltage phasor, your current phasor is going to lag by 90 degrees. So what that means is the voltage peak and the current peak are not at the same time. So if the voltage peaks at one point, the current peak will happen at a certain period after the voltage peak. So that is very bad in terms of reactive power. That can be another video sometime. But ideally, you want these to be parallel. If you have a resistor, they're pretty much in parallel. So if you have a resistor, how that's going to be is your voltage and current phasors are going to be pretty much in sync. All right. So when you have a lagging power factor like this is what we could call a lagging power factor. So by adding a bunch of capacitors to your circuit, you can try to minimize this and sort of get the current phasor in line with the voltage phasor. So that is another application of capacitors. Without ado, let's go ahead and get to solving some problems. All right.